Most people think that the multiverse means infinite versions of you, other lives, other choices, other worlds where everything played out differently. But that's not what physicists mean at all, because the real multiverse isn't about alternate versions of your life. It's about something far stranger, and it comes from our best theories of the universe and reality itself. And in some cases, scientists now think that it might even be testable. Here at New Scientist, we've been following the science of the multiverse for decades. And what's emerging is not just one idea, but several very different versions of reality that all point to the same unsettling possibility that our universe may not be the only one. In this video, we're going to explore the real multiverse, from quantum many worlds to the vast cosmological bubble universes, and the experiments now beginning to search for evidence of them. Because once you strip away all the sci-fi, what physicists are proposing is not a fantasy. It's a completely different way of understanding reality, and it leads to a question that's far more unsettling than any movie. If these multiverses really exist, is our universe really special, or just one of countless random outcomes? Chapter 1. The multiverse is not what you think. In films like Sliding Doors and Everything Everywhere All at Once, depictions of parallel universes draw on our innate curiosity about the paths our lives might have taken. Protagonists meet variations of themselves who made different decisions, who possess distinct abilities. The idea that all of our unfulfilled aspirations, all the lives not lived, are realized somewhere out there in the multiverse. Like, what if I chose to study chemistry instead of physics at university? The horror. But this is not how physicists think about the multiverse. Unlike the movies, the scientific notion of the quantum multiverse has little to do with our personal decisions, never mind our wildest fantasies.
Sadly, when physicists talk about the multiverse, they mean different things, and none of them are the things that people have in mind from watching the Marvel movies, etc.
No, it's even weirder than that. Instead, it stems from physicists' attempts to make sense of the reality we do experience. The quantum multiverse is actually taken quite seriously in some physics circles as a way to resolve one of the biggest conundrums in physics. Now, I need to take you back to the 1920s, when physicists were struggling to parse a new theory of reality called quantum mechanics. This new theory describes the vanishingly tiny and staggeringly strange, the realm of atoms and subatomic particles. The weirdest thing is that these particles appear to exist in a superposition of many possible states all at once. Let's say we were trying to pin down where a particle was. Now, we can't pin them down exactly like we can ordinary objects. Instead, we see that particles act like they're in multiple places all at once. That is until you measure them, at which they suddenly take on definite properties, like they suddenly end up here and only here. The Schrödinger equation captures this vagueness, incorporating a mathematical concept called the wave function to encode all possible outcomes. It allows us to calculate the probability that our particle will manifest in a particular place when we measure it. But it can't tell us for certain the outcome of a single measurement. In other words, all we have until we look are probabilities. So how does the concrete classical reality that we see, which itself is ultimately made up of atoms and particles, emerge from this fuzzy quantum netherworld? Physicists call this the measurement problem, and it is the central mystery of quantum theory. You might think that this isn't a big deal. After all, I could open up the weather app on my phone and you could say there's going to have a 75% chance of sunshine in London tomorrow. Yeah, good luck with that. But the weather just does take on one definite outcome. So isn't that the same thing? Not at all. Remember, quantum objects behave like they're in a superposition of possible states until they're observed, a mixture or combination of possibilities. That's distinct from something like the weather, where the reality reflects only one of many scenarios that are possible, and the probabilities that I see on my weather app, they arise mostly from ignorance. In quantum mechanics, the probabilities are baked in, encoded in the wave function. In fact, it should be mathematically impossible for the wave function to just go from a mixture of these different possibilities to just one.
The measurement problem is just the question of what do you mean by the phrase measurement in quantum mechanics. When you say, when I measure a system, its wave function collapses and I get a definite outcome, like the cat's alive or the cat's dead or whatever, what counts as a measurement? Does it need to be a human being? Can it be a video recorder or what? We have no firm answers to those questions.
Now, one way to deal with this problem is just to say that there isn't a problem that we need to solve. The wave function, these probabilities that it represents, it's all just a kind of mathematical shorthand, that it's not actually representative of reality. That's what many people call the Copenhagen interpretation.
The phrase the Copenhagen interpretation is sometimes used to talk about a certain approach to the quantum measurement problem. It's a little bit problematic because no one agrees on what the Copenhagen interpretation actually is. People like Niels Bohr and Werner Heisenberg pioneered it, but they didn't agree with each other or even with their own selves from paper to paper sometimes. But it's the basic idea that there is something fundamental about measurement, right? That we describe systems mathematically in a certain way in quantum mechanics, but if you're a hardcore Copenhagen person, that description of the system when it's not being measured doesn't really describe the real world. The real world is just the measurement outcome.
In the 1950s, Hugh Everett was grappling with this problem. Everett suggested that when the wave function snaps into a single definite outcome, something that we call the wave function collapse, those other possibility scenarios don't just vanish. Instead, he arrived at an astonishing conclusion, that every time a measurement is made, all possible outcomes contained in the wave function are realized in many separate worlds that branch off from our own. So rather than a collapse, there's a split, avoiding the mathematical impossibilities from before. Essentially, Everett's bold move was to say that all different parts of a quantum superposition really do exist. It's just that they exist in separate, non-interacting worlds. This is known as the many worlds interpretation of quantum mechanics, but you can call it the quantum multiverse.
It says when I measure a quantum system here in my lab, and I get two possible different results, I will get two different universes. The one universe that I was in splits into two, and in each one of the two different ones, I now have a definite measurement outcome.
To be clear, it is an interpretation that a good number of bona fide physicists take seriously. But since these branching universes never really interact with ours, the idea can't be tested with observations. And that leads to a couple of tricky questions. First, if all of these other worlds really exist, where are they? And more importantly, why don't we ever see any sign of them? The answer is not what you might expect. In fact, these other worlds aren't out there at all. Chapter 2, where are these other worlds hiding? The short answer is that they're not located in physical space. You wouldn't find them lurking just beyond the observable universe, even if we could somehow see beyond the cosmic horizon. Rather, they exist within a larger mathematical structure, because what we call worlds here are actually just different components of a single wave function, that of the entire universe, encoding all possible outcomes of all quantum measurements or observations. The branching involved is not a spatial separation, but division within the structure of this wave function. This is why some of today's leading many worlds proponents, including Sean Carroll at Johns Hopkins University in Baltimore, have argued that talk of parallel worlds is actually misleading because it suggests physically separate locations.
There is no physical location of them because location in space is something that exists in each world. The many worlds of quantum mechanics simply exist simultaneously.
So these worlds have absolutely no physical connection with our own, which means you really don't need to worry about the fate of your doppelgangers. But this also helps to explain why, if every quantum possibility is realized, the singular reality we experience is not completely incoherent or chaotic. Why we could exist in a quantum multiverse without ever noticing its infinite weirdness. The explanation involves a phenomenon called decoherence, the process through which quantum objects or systems lose their quantumness, including superpositions, as they interact with their surroundings. Basically, the larger a quantum object or system is, the more it interacts with other objects, and the faster its quantumness vanishes. In the context of many worlds, branches are decohered relative to each other, effectively isolating them from one another, but they're never completely destroyed.
That's decoherence. Decoherence is when a quantum system that was in a superposition of two different possibilities becomes entangled with the environment around it. And the relevance of that to many worlds is that that's the moment when the world split. When decoherence happens, when your system becomes entangled with the environment, now that decoherence, that entanglement is irreversible. So basically, classicality, the fact that the classical Newtonian universe is such a good approximate description of reality, is because it's those quantum mechanical states that remain robust and unaffected by becoming entangled with their environments.
Today, most physicists agree that this is why the everyday world looks classical rather than quantum, but it might also apply to the many worlds scenario. The thing is, you could argue that the insistence on separate, non-interacting branches of reality means many worlds is deliberately constructed to explain why we don't see contradictory outcomes. The maths of quantum theory only gives you the wave function governed by the Schrödinger equation, but it doesn't explicitly say the universe splits up into independent worlds, and many worlds says nothing about why branching works that way. For instance, at what level does branching occur? When are branches sufficiently decohered from one another that they stop interacting with each other? It's very difficult to answer these questions because, from the outset, we can't ever measure or ever interact with other universes. In this picture, reality in each and every branch appears consistently classical rather than chaotic. But each observer, each of us, can only ever experience one branch. This is why, even if we live in a quantum multiverse, our reality wouldn't look weird or confusing at all. The other quantum worlds will always be beyond our perception, but that's not the case for another form of parallel universe. Now let's look at a version of the multiverse that might leave traces in our own universe. Chapter 3, the universe that keeps making new universes. To get to grips with this other multiverse, we need a drastic shift in scale. From the tiny realm of the quantum theory to the biggest of all pictures, cosmology. Now, this isn't related to the many worlds interpretation of quantum mechanics. The cosmological multiverse refers to, quite literally, bubbles out of cosmic inflation. The idea is that in the split second after the Big Bang, space-time itself expanded exponentially, a stupendous stretching that explains why the universe is unfathomably uniform and smooth at the larger scale when there's nothing in the Big Bang picture alone to suggest why that should be the case. Inflation is an incredibly successful theory and widely accepted. The problems and the fun began when cosmologists realized that inflation could be an ongoing process. In this picture, quantum effects can randomly cause some patches of spacetime to continue expanding very quickly, creating bubble universes that expand faster than our own. Importantly, because the background universe continues to balloon, new bubble universes are constantly being formed in different regions, with each effectively isolated from the others because the space between them expands faster than light can cross. Eternal inflation, therefore, creates an endless froth of bubbles, an increasing number of separate universes. Cosmologists call this the inflationary multiverse. As if that's not mind-boggling enough, you also have to get your head around the idea that these other universes could look nothing like our own. That's because some physicists have also decided to throw string theory into a multiverse mix. String theory operates in 10 or even more dimensions. In addition to the 3 of space that we're familiar with, plus time, there are 6 more dimensions that would be scrunched up into unimaginably small spaces. In our universe, they form a particular configuration which determines the properties of our particles and our laws of physics. But they can form at least 10 to the power of 500 different configurations, meaning that universes can fall into that many categories, each with different particles and laws of physics. You could, for example, have a different speed of light. Now, some of these bubbles just pop or stop existing because not all configurations of physical laws are conducive to stable pockets of spacetime. In fact, most configurations aren't. Our universe in particular has constants that seem finely tuned to us existing in it. If you were to visit another universe, even for a moment, you'd decay in an instant. But you can't, of course. Even if there is another universe conducive to our sort of life, you could never get there, even if you traveled at the speed of light forever, because you would have to travel through a piece of space that's still inflating, meaning that the distance between bubbles grows faster than the speed of light. But unlike quantum many worlds, the inflationary multiverse would at least exist in physical space. And because of that, some physicists reckon it might even be possible to find observational evidence of its existence. That's right. Evidence of a multiverse, something that could turn physics on its head. Chapter 4. Can we actually find new evidence? Okay, so the logic behind the inflationary multiverse seems sound enough, but there also happens to be zero empirical evidence for its existence, which is why some physicists have made it their mission to find some. The most obvious option is to search for a fingerprint from other universes in our own. If the hunt for evidence of new physics excites you, then head over to our podcast channel for an even deeper dive. One of our newest episodes explores a number so vast it stretches past the limits of the universe itself. A discovery that forces mathematicians to confront what can and can't be proven. Today's episode has you thinking about the boundaries of knowledge. This one goes even further. Powered by New Scientist's decades of reporting, The World, the Universe, and Us is our award-winning weekly podcast hosted by Dr. Rowan Hooper and Dr. Penny Sarshek. It unpacks the most important developments in science each week, covering everything from consciousness and climate to dark matter and intelligent life. The podcast has its own dedicated channel, which means every week we can respond in real time to the biggest breakthroughs in science, bringing in expert guests that unpack what the headlines actually mean. We won't be publishing the podcast on this main channel anymore, so click the link in the description to subscribe to our new podcast channel and make sure you don't miss an episode. Now, back to the quest for evidence of a multiverse. We know that the inflating space between bubble universes would quickly hurl them apart. If two are formed sufficiently close together, however, it's possible they could have collided before being separated, and we might find evidence of that in marks or scars left behind in our own universe. Most cosmologists agree that the best place to start looking is a cosmic microwave background, or CMB, the faint afterglow of the Big Bang. In fact, a team led by Hiranya Paris at the University of Cambridge in the UK has proposed that the colliding bubble universes should have left circle-shaped scars in the CMB. They even created an algorithm to comb through images of the CMB for such imprints. What they found was promising. 4 patches of the sky were compatible with the shape of collision imprints, but it wasn't evidence. There's just too much uncertainty in our understanding of the rate at which these new bubble universes should form and the probability that they would collide to make precise predictions. This is why another group of physicists have recently begun trying to make replicas of this process in the lab. To understand how this experiment might work, we need to return to the quantum weirdness for a moment. I want you to picture a landscape of hills and valleys with a ball, representing our universe rolling around. When our universe ball is at the top of a hill, inflation is on, and it's very rapid. When it's at the bottom of a hill, inflation slows or stops completely. These hills and valleys are like an on and off switch for inflation. If you want to know the technical term for this, physicists call this landscape an inflaton field. But I prefer the term inflation roly-poly, and it's not actually a physical landscape, but hang with me. The lowest valley in this inflation roly-poly is known as the true vacuum. We have reason to believe that more than one vacuum state exists, but also that most are false, meaning that they're not the lowest possible energy. These would look like roly-poly valleys that are locally deep, but not the deepest that exist. These valleys are known as metastable. Imagine our universe ball is in one of these false vacuums. Quantum mechanics makes it possible for us to tunnel through the walls of the valley to the other side, where we could suddenly start rolling to a lower energy state. Cosmologists call this a false vacuum decay, and they care about it because it would explain how our universe and maybe others first began. For instance, what if our universe started out in a false vacuum before tunneling and reaching a true vacuum, which is what we observe today? The trouble is that we can't know for sure, and unless we know the details of this process, we can't trust our theories. Luckily, almost a decade ago, physicists in New Zealand discovered that under the right conditions, the equations describing false vacuum decay in the early universe can be simulated in a kind of exotic matter called a Bose-Einstein condensate, in which bubbles akin to a true vacuum are created. By studying the formation and behaviors of such bubbles in the lab, we can learn about how multiple universes might have formed, including the chances they would collide. This insight forms the basis of an exciting new experimental project led by Zoran Hadzibabic at the University of Cambridge, designed to be a direct analog of cosmological vacuum decay. The first stage produces the Bose-Einstein condensate by making potassium atoms colder than anything in the universe. The next involves preparing the condensate in a metastable vacuum state and waiting, and finally watching as expanding bubbles of true vacuum form. Hadzibabic and his colleagues reckon that this gives us a proxy for the otherwise unobservable processes thought to have first created new universes, and a chance to re-evaluate whether or not those unexplained patches in the cosmic microwave background really could be imprints from the multiverse. All of which goes to show that one of the major criticisms of inflationary multiverse, namely that it is too untestable, may no longer be true, because our own universe may already be the evidence. Chapter 5. Why our universe works at all. Remarkably, it might even be possible to test whether the inflationary universe really exists without having to directly observe it. Remember when I said the most configurations of physical laws are super unstable? Well, it turns out that our universe is actually one of the few with the perfect combination of physical laws and constants to sustain the existence of matter, and by extension, life itself. If things were even slightly different, life as we know it wouldn't exist. It seems odd that we should be so lucky, or as physicists put it, our universe seems mysteriously fine-tuned. The multiverse offers an explanation. If there are an infinite number of bubble universes, a few of them should, statistically speaking, have the conditions necessary to support life, however unusual those conditions may be. And humans will naturally find themselves in one of those. This is what we call the anthropic principle. Humans can only exist and observe in a universe compatible with our existence, so of course we think it looks fine-tuned. And it opens the door to a falsifiable statistical prediction. If there really are many universes, each with different physical constants and laws, and if observers can only arise in some of them, then we should expect to live in a universe that's not merely just compatible, but unusually conducive to life. In other words, our universe should be near optimal when it comes to habitability. McCullen Sindora at the Blue Marble Institute for Space Science in Seattle has found a way to test that by modeling how habitability depends on the values of physical constants, looking at each scenario to figure out how many stars form, how long they live, for instance, and how often planets form and how easily life could emerge on them. Sindora can then ask, if these constants varied across universes, where would life and conscious observers be most likely to appear? If our universe is not right at the top of that list, that could count as evidence against the multiverse hypothesis. The big problem, of course, is that testing these predictions relies on us finding life elsewhere in the universe to give us a sense of how common life is here. And we haven't, at least not yet. Chapter 6, the real implication of the multiverse. Ultimately, we don't know if the inflationary multiverse exists, and the truth is that we'll probably be waiting for a good while until we find any evidence at all, never mind something everyone can agree on. From the multiverse that physicists describe using quantum theory, where reality we see is just emergent from a vague fog of probabilities, to the multiverse that seeks to explain how our universe began and evolved into what we see today, these ideas that we've explored in this video are some of the most interesting and polarizing in modern physics.
All of these are very controversial theories, so the many worlds interpretation of quantum mechanics is certainly not a majority view. It's a very, very common view within certain closely selected subsets of physicists who think about quantum cosmology and things like that. But most physicists don't subscribe to it. But on the other hand, most physicists don't think deeply about the measurement problem and the foundations of quantum mechanics at all, so they don't have a favorite way of thinking about it.
This is the boundary where physics and metaphysics begin to blur. Some people would rather steer clear of these gray areas, but we at New Scientists love asking what science can tell us about the nature of reality. Here, science is way more interesting than science fiction. And while the gap between the two might be part of the reason some people dismiss the multiverse out of hand, what we've learned along the way here suggests that we should keep an open mind. There was a time not so long ago when black holes were dismissed as science fiction, and now we're taking photographs of them and uncovering what really is inside. But once something crosses the edge of a black hole, our understanding of reality starts to break down completely. And that's exactly what we explore in this video here.